Hi, class. This week we are going to cover the endocrine responses to resistance exercise. So, if we think about the physiology, we often think about structure, but it's really important to consider the hormones and how the hormones actually are going to change structure as well as what they do during the resistance training process. So, our objectives for this lecture are going to be understanding the basic concepts of endocrinology, including what hormones are and how they interact with each other, and the target tissues. Explain the physiological role of anabolic hormones, describe hormonal responses to resistance exercise, and understanding how training programs and/or structure organization can influence human endocrine responses in a positive way to benefit your training. All right, so a couple things we just have to make sure we understand what are hormones and this endocrine system. So hormones are going to be those chemical messengers that are synthesized, stored, and released into the body by endocrine glands and certain other cells. So if you remember biology, looking over here on the right, we have several of the organs in the endocrine system. The endocrine system is going to be made up of those endocrine glands that these glands specialize in releasing hormones into blood to elicit some sort of adaptation. And it's really important just to sort of remember that hormones kind of make us who we are and how our hormones function. So we'll talk a lot about that as it relates to resistance training. But a couple examples here, and this is obviously female, but you also see in the lower right-hand corner testes for male. So we have ovaries in female working from the bottom up, the kidneys, the pancreas, the liver, the adrenal glands, heart, parathyroid glands, thyroid glands, pituitary glands, and the hypothalamus. All have some sort of play in the adrenal family, and these would be, in the endocrine family, and these are endocrine glands. The principal endocrine glands of the body, along with the other glands that secrete hormones. We'll talk about that. And then hormones are clearly intimately involved with protein synthesis. So that's kind of really the big play here when it comes to exercise phys and really the role of the hormones, because we're looking to influence protein synthesis, which is simply defined at the rate at which our bodies can build new protein structures, cells, repair. So obviously, in our case, we're really talking about muscles, connective tissue, and even to some extent some bone, but primarily those tissues. Hormones, yes, I said that already, and they're also part of the degradation of mechanisms that are part of muscle adaptation to resistance exercise, and they're going to include anabolic hormones, which promote tissue building, and catabolic, which degrades protein cells or would ultimately degrade protein tissue. And those are sort of the two functions of this of this endocrine system. All right, so sort of understanding how do hormones even function, right? So these concentrations get put into the bloodstream depending on stimuli, depending on growth, depending on, puberty is a big one. But essentially, these chemical composition, these chemical components are in the blood, and they have different shapes. And so there's this lock and key theory of how do certain cells absorb certain hormones and other cells don't absorb the same hormones. So if you look at this visual here, you're going to see this kind of idea that hormones have a specific shape that can fit consequentially into specific cells and can't fit into other cells based on the receptor site on the cell itself. So you see hormone A up there, which looks like it would fit perfectly in receptor A. Hormone B in the middle fits into surface receptor B. And then hormone C fits in receptor C. But you also see over here the hormone in the sort of upper right-hand area, hormone with potential cross-reactivity with receptor C. So because there's a little piece there that could fit into receptor C in the right hand, sort of the middle, the smaller square, there's some potential for a little bit of disruption. So it's not always a perfect thing, but essentially this is how we have to think about hormones, how hormones can signal or strategically connect to certain types of cells in our body and not have an impact on other types of cells. So the inability of a hormone to interact with the receptor is also called downregulation. So that's what we were just kind of talking about. In this example, you're going to see a little bit cleaner picture. You can imagine that's actually the surface layer of a tissue in blue with the little lines. So the blue little circles going across in section 2. The top is section 1 is going to be all your hormones. They're going to have different shapes, and then you're going to see inside those receptors the purple portion, right, the different shapes. And then at the bottom, once the hormone is connected, that releases some sort of signal, which you're seeing in that left-hand side in 3. If the receptor can't interact with it, that's just called downregulation, and that can happen for a few different reasons. Sometimes some structural issues, sometimes some disease state stuff, but ultimately, to the point up here is that the alterations to receptors binding characteristics or the number of receptors can be as dramatic in adaptation as the release of increased amounts of hormone from the endocrine gland itself, which would be sort of at the bottom there in green. Okay, a big classic one. We talk about steroids. Steroids are synthetic hormones, synthetic testosterone. So testosterone that's been basically altered in some way, shape, or form that is going to be anabolic, meaning it's going to build protein. They're going to be fat soluble and passively diffuse across the cell membrane. So don't get too worked up over this picture down below. It's just something to kind of visually look at, kind of the big picture of what all these hormones can do. So typically steroid migration is going to migrate into the target cell by either testosterone in skeletal muscle or dihydrotestosterone in sex-linked tissues. Only one hormone pathway, testosterone and dihydrotestosterone, is targeted for one cell, but the two are shown together in this diagram. Each has a different physiological outcome. So if you look over here, you're going to see on the left-hand side at the very tippity top in green, luteinizing hormone. Luteinizing hormone is responsible for signaling to the testes to produce testosterone. Then testosterone is released, and then you're going to see it's going to pass through some of these cellular structures. It's going to find its particular cell that it fits with in the lock and key, and it's going to start doing some signaling that happens inside of the cell. That might have an effect on anything from metabolic effects, such as protein synthesis, to gonadotropin regulation, so how much growth is happening, spermatogenesis, which would be the development and increasing of sperm production, sexual differentiation, so what makes us male, female, Wolffian stimulation. I looked it up. I couldn't remember. I'll have to get back to you on that one. External virilization, right? Thinking about how effective our sperm will be. And then we're getting into something as simple as sexual maturation at puberty. So the hormones go in and are going to have a variety of impacts on the human body. But each one is going to be sort of dependent upon the cell, and what the outcome of that hormonal release is going to be determined by the type of, let's use say steroid in this example. But generally testosterone, estrogen, progesterone, and cortisol are going to be our primary fat soluble muscle building, when we look at this, and or tissue regulation tools, hormones. All right, polypeptide hormone interaction. So these are a little different. They're water soluble. They're made of chains of amino acids. So these two examples of this would be growth hormone and insulin. Typically, polypeptide hormones interact with receptors via the cytokine activation. Don't get too worked up over all this stuff. It's just kind of to understand that obviously this is a very complex system that has a lot of moving parts. Although hormones bind to an external receptor, a secondary messenger is activated that can enter the cell nucleus. So you see in this example here, where in the first example, the hormone went through and actually had that reaction. If you want to scroll back, you'll see it went through and the hormone actually had the reaction inside of the cell. This one's a little different where the interaction happens on the outside of the cell membrane. You see that in green, it connects to the receptor site. And then there's some sort of reaction that happens inside of the cell outside of the hormone interaction at the outside of the cell. I gave you those examples up there, growth hormone and insulin, but another one would be glucagon, which is made by the liver and is a glucose, emergency glucose fuel supply. Okay, a couple more categories here. We have amine hormone interactions. They're water soluble. They synthesize from amino acid tyrosine. Example would be epinephrine, which we'll talk about a little bit later, and dopamine. These are things in the brain, or tryptophan, which is serotonin. It's kind of like puts you to sleep, relaxes you. They bind to membranes via secondary messengers, not regulated by negative feedback. And here are some of those examples. Also melatonin, epinephrine or norepinephrine, which is going to be your fight or flight hormones. And then that dopamine, which is that feel-good brain hormone. So now with heavy resistance training and hormonal increases, hormones are secreted before, during, and after resistance exercise bouts due to the physiological stress of resistance exercise, right? So obviously the more rigorous it is, the more potential secretion you can get. As few as 1 or 2 heavy resistance exercise sessions can increase the number of androgen receptors in the muscle. So the receptors that can receive testosterone and muscle building signaling. The specific force produced in activated fibers stimulates receptors and membrane sensitivity to anabolic factors, including hormones, which ultimately leads to muscle growth and strength changes. So this happens in men and women. And I put this set of pictures up here for the women in the room. Many of the men are generally historically more comfortable with heavy resistance training. A lot of women are concerned that it's going to make you big and bulky. I've talked about this quite a bit. If you want to maintain your overall ability through the rest of your life into your old age, you need to do resistance training because of the rapid rate and declination of tissue, muscle tissue, bone tissue, hormone concentrations. All of these things change for all of us at some point. And you can see over here on the right-hand side, this is obviously woman's deadlifting. Now, she's not pulling a gazillion tons of weight, but she is lifting heavy weights. I believe I forgot to pull the info on this. I think she's in her 80s, early 80s. So you're going to look at her and be like, wow, she doesn't look 80. No, she's been doing all of this good stuff, and we're going to see the impact of this on the body. The other piece to this, I think we have to reconcile for the women in the class and any women who really have this concern and fear of gaining massive amounts of muscle. You just do not have the hormone concentrations to do that. You might say, well, what about female bodybuilders? And I've said this before, they're taking more testosterone than probably in total in their body is equal to all the men's total testosterone in this class. So they are supplementing testosterone through injections, through steroids, through not just 1 or 2, but multiple types of hormones that they're stacking in order to elicit this really muscle building environment that no woman can do naturally. It just doesn't happen that way. So I just want to encourage resistance training. I'm stoked that we have so many females in the class. And I guess I just skipped I skipped to the next one. So we're just going to keep going. I'm excited I have so many females in the class. But I want to and many of you are very interested in resistance training, which is great. So I'm not trying to downplay anyone's, pointing anyone out. It's just really important, in my opinion, to reiterate the importance of resistance training from a physical structural standpoint, but also a hormonal response. So we'll get into that with each of the hormones and talk about the differences between males and females. So here's some more mechanisms of hormone interaction. So the combination of many different mechanisms is thought to stimulate exercise-induced hypertrophy, muscle size. And look, this is still research that's happening. It's not fully understood. Molecular signaling includes hormones, including hormones is involved in this process, right? So when we signal molecularly, what do I mean by that? In the human body, force is the language of tissue. Let me repeat that. Force, effort, stress is the language of tissue. And the hormonal system, the endocrine system, will respond accordingly to facilitate changes into those tissues. So you see on the left-hand side here, I have healthy muscle, which would be bigger, thicker. That's hypertrophied muscle. And below that, atrophied. Opposite of hypertrophy is atrophy, so muscle getting smaller. The big difference is really between the two muscle cells is the healthy muscle, the more hypertrophied muscle, is going to have a lot more density of muscle fiber. A little bit, you see 1% of adipose, that's going to be fat, and then 4% of its connective tissue. So in between each of those little cells that you see on the left-hand side are connective tissues, paramecium, endomecium, and epimecium, which is a little bit more of the anatomy, which we cover in our functional anatomy course, our Kin Major 102. But just understand that all of these little tiny cells have to be held together with connective tissues. That's going to make up a part of the muscle density as well. But if you look at the atrophied muscle, there seems to be more space. It's not space, it's more fat, more adipose tissue, and a little bit more connective tissue as well. Clearly less muscle fiber. So this kind of idea of like what is hypertrophy, it's really just muscle size, and sort of at a cellular level, you get a little bit more appreciation for the differences between training, having muscles that are consistently training and involved in activity in some capacity, physical activity, versus muscle that's not being used as consistently. So the signaling of how these fibers are going to change comes from the hormones. Hormones are an integral part of this process, and it's influenced by neural factors, the nervous system, that provides important signals to the skeletal muscle and thus can augment the muscle building process or the protein building process. So think of the brain is signaling to the body to do something through the nervous system. But if I continue to do something and the stress that I'm imposing on the tissues is more than it's accustomed to, and I consistently do that, we're going to start to see hormonal concentration changes, as well as ultimately resulting in greater changes in muscle as well. All right, so bigger slide here. I've got a smaller slide, so I'm going to make sure I stay in it. Hormonal changes in peripheral blood. So now we're talking about the blood supply that's just running through our body. Our peripheral concentrations of hormone in the blood do not indicate the status of various receptor populations or the effect of hormone within a cell. Remember, you see the cell, you think, okay, well, if I have higher concentrations of the hormone in my blood, I should have equal amounts of receptors that are ready to take it. Well, that doesn't always necessarily work out. It is assumed, however, that large increases in hormonal concentration indicate higher probabilities for interactions with the potential receptors that you have. So it's just kind of an interesting sub-theme in this, is that just because you put more in doesn't necessarily mean it's always going to bind in the exact way that it might bind in someone else. It is assuming that you've got the equal amount of receptors, right? So now we get into some genetic variability. An example would be testosterone concentration. So bound testosterone is bound doing something versus free testosterone, which is floating in the bloodstream. When you get a testosterone test like this looks like on the right-hand side, often they're looking at total testosterone. Well, total testosterone doesn't tell you how much free testosterone is floating around in your blood. And so that is a different test that has to happen. And so that's an example of a test not necessarily kind of looking at what you might need it to look at. And there's normative data around where testosterone should be for all human beings. And so doctors can compare and contrast. And by the way, the doctor who does all the hormone stuff is called an endocrinologist. That is their domain. They are the hormone doctors. And they are pretty remarkable because they have a much deeper understanding of this system than I could ever have. But from an exercise perspective, I can certainly give you some insight that maybe they didn't necessarily get, but they probably have a much better understanding and how to explain it. So it is what it is. All right, so a couple other things. Physiological mechanisms that contribute to the change in peripheral blood concentrations of hormones with exercise. You're going to have circadian patterns. So how you sleep, right? How you get into your circadian rhythm of waking up and sleeping will have an influence on how much hormone is being generated or not being generated. Fluid volume shifts. So now we're talking like specifically, I think it's easiest to sort of equate with women. There might be time when there's going to be more hormone concentrations because there's more fluid retention. And it's really, the fluid retention is driven by the hormone concentrations. Tissue clearance rate. How quickly can tissues move hormone concentrations? Venous pooling of the blood. So how effective are your capillaries, arteries, and veins at kind of moving the blood through the system? And do you have blood pooling in any particular area? And then hormone interaction with the binding protein. So does the hormone actually do something once it's there? What reaction is it having? So the key point here is that hormone responses are tightly linked to the characteristics of resistance exercise protocols. I don't know why that's there. We're about to get into this. I don't know why I put that there, but just bear with it. All right. Adaptation of the endocrine system. So the two examples of types of adaptations that are possible can be the amount of synthesis and storage of hormones. So how much can the hormones create? Like how much more hormone is generated and created as a result of resistance training. So this is something that can change. And then the time needed for clearance of those hormones through the liver and other tissues can be increased. How many receptors are in the tissues, right? We can have a little bit of influence on that, and that will adapt, but depending on how much training we're doing. Changes in the contents of the secretory cells in the glands. So how, again, another variable, minute variable that can change. And the degree of interactions with the cell nucleus. Ultimately, the cell nucleus is going to be the signaler for what's going to happen, giving the sort of the command to the cell. So how impactful is the interaction of the hormone with the nucleus of the cell? All right, so let's start with our first hormone, which is one of our, obviously our primary anabolic hormones, is going to be testosterone. It's heavy resistance training using 1 or 2 repetitions in low volume. Low volume meaning heavy weight, low reps, which may not cause any changes in testosterone concentrations after a workout, could potentially still increase the absolute number of receptors and thus binding sites available to testosterone. So even if you do lower repetition, using 1 or 2 reps, low volume, and that's kind of what you're doing, you're going to have some sort of physiological change that might result in changes to the binding sites. However, the effect on the receptors has not fully been elucidated, which is the fancy term, not been studied enough. So key point here is large muscle group exercises using an adequate volume of total work result in acute increased total testosterone concentrations for men. So even if we do low stuff, there are some changes, but we want to make sure that we're going to have some, when we talk about hypertrophy as an example, muscle size, it's going to be anywhere from 6 to 12 repetitions with about anywhere from 30 to 90 seconds of rest. And so you have to remember, though, when you're picking your weight, let's use 10 reps as an example. By the time you get to the 10th rep, it has to be pretty darn hard, meaning you're eliciting the overload. If you have reps in reserve that you can keep going, the weight isn't hard enough. So you're not actually truly working in that hypertrophy phase. And we'll talk about this later because we'll have a little training assignment towards the end of the class where we'll kind of build a program based on some of the variables that we want to manipulate. All right, so the other exercise variables that can increase serum testosterone concentration. So large muscle group exercises such as deadlifts and squats, heavy resistance, 85 to 95% of your 1 repetition maximum, moderate to high volume of exercise. So if we do like more sets of exercise, That's going to accumulate more total reps. And I'll get into this. We'll do a program design deal at the end, and we'll talk about how these variables can be manipulated inside of a training program. So just sit tight for that. Short rest intervals, 30 seconds to a minute. And we even know in the hypertrophy phase, probably anywhere from 30 to 90. But from an anabolic testosterone serum concentration, we probably going to want to stay with that 30 to 1 minute and then get right back into our next set. 2 years or more of resistance training experience. So we've got to build some quality time under the bar, so to speak. And we tend to see this with people who have a longer career in cumulative career in weight training. Sometimes it's called old man strength. And the reality is it's years under the bar allows the tissues to fully adapt and really maximally benefit. So all of the physiological adaptations. So early on in your training career, you might notice as you get a little bit older or longer in your training age that your muscle quality changes because you actually have some different physiology happening at that point because of the years of work put in. Continuing on with testosterone here. So for generally free testosterone versus sex hormone binding globulin. So free test accounts for about 0.5% to 2% of total testosterone, and that was what we were talking about earlier. That free testosterone is available to be used. Thus, higher total testosterone concentrations allows for more testosterone or freer testosterone. So anything we can do to increase our testosterone, which is going to be lifting heavy weights, is going to allow for greater amounts of free testosterone. Heavy resistance exercise, example, 6 sets of 10 reps at 80% of 1RM can acutely increase free testosterone in men and women, although increase in women is much smaller for women. So that's, again, a reminder, yes, women make testosterone too, but not nearly the amount that men are able to make. But that's also important, as you look at this picture here, you might say, well, geez, that woman is a little bit too muscular for my taste. Might be. I would say on the left that guy's too small for my taste. I would say that the woman on the right looks great. I think it's fantastic that she's pulling, it looks like 315. If those are one set of, that looks like at least 225, 275. Because you see the middle bumper plate there is a little thinner. It looks like it's 245s plus a 25. So that'd be 275 pounds she's deadlifting. And good for her. She's got a smile, and that's super impressive. But that's going to come with years of training. All right. Now, for women specifically, though, women have about 15 to 20-fold lower concentrations of circulating testosterone than men do. The testosterone concentrations can vary substantially between individual women, as some women secrete higher concentrations of adrenal androgens or testosterone, protein-building stuff. So you might look at this woman and say, well, she's pretty muscular. Well, she might be a woman that has a little bit higher concentrations of testosterone than the next woman. This is where individuality comes in. So it's not only just genetics like muscle structure, but also now we're talking about hormone concentrations. When all of this works perfectly, we build the best athlete for weight training. And those are the people that we typically see, the big influencers, right? And their physiques look a certain way because they've sort of found their sport. Now, kind of continuing on with anabolic hormones, total testosterone and free testosterone, you're going to see the purple line there is men. This is a response to 6 sets of squats at 80% of 1 rep max with 2 minutes rest in between each set. And you're going to see before on the left, the first column, pre, mid, IP, which I'm not sure. I think that's in progress. Post 5 minutes, post 15 minutes, post 13 minutes, post 70 minutes. And you're going to see the spike in, for men, significant increase. And you're going to see that there is a slight increase for women, but it's very small. So just knowing if you're not taking anabolic steroids, you're not going to be able to develop really maximal muscle mass. So some training adaptations because of testosterone include, so this increase in testosterone is a response to the demands of the exercise, so how we structure it. how intense it is, the protocol, how we organize the exercises, and the receptors. Like as an example, if I do cardio before my squats, let's say I run, for 30 minutes at a pretty good clip, that's going to negatively impact my ability to squat because my legs are going to be fatigued. So the testosterone concentration potential is going to be much lower because I'm not going to be able to push as much weight. So just your organization of your training program becomes a huge critical component to maximizing the hormones and allowing the hormones to do what they need to do based on your long-term goals. And so I'm kind of getting ahead of myself, but it says the receptors either increase binding to use the elevated testosterone or they do not due to lack of need for the signal to increase muscle-related metabolism. So you've got to be training pretty darn hard to tell the tissues to use the hormone, the testosterone. If you're not training hard enough, even if you get some increases in serum testosterone, it doesn't matter. It's not going to do anything because there's no stimulation. There's not enough signaling to tell the system that it needs to actually start to build more muscle mass. Other receptors on the target tissues, example, the nervous system receptors and satellite cells that do some other things, may be more affected at certain time points in training depending on the window of adaptation available in the targeted muscles. Now, I put this thing on the right here. This guy's holding a supplement. You put a lean guy who's probably been airbrushed and you say, this is going to increase your testosterone, this random supplement that's not FDA approved because we put a muscular guy on there. Right, many of us, myself included, when I was young, I was like, "Yeah, I got to get these supplements." But the supplement industry is frankly a giant scam because there's no real FDA approval on any of it. They can't make salacious health claims. But what they do is promote with visuals all of this stuff, scientifically formulated. Oh, it must be great. That's meaningless. There's been no research to back any of this. This is just a combination of ingredients that have been, quote, proven based on what study? I have no idea. I doubt any studies, cumulative randomized control trials are going to say that this stuff actually works. It's just not that. It's just not the world that we live in. Most supplements, except for creatine, as we talked about, are going to be bunk. They're not going to work. So just be mindful of this stuff. The best thing you can do is make sure you're getting enough rest, getting enough in training intensity. That's what you got to focus on and put years in to build up these physiques. All right, I'm going to get off that now. Growth hormone. Here's another type of hormone. It's important for the normal development of a child. So part of child development, maturation, children and teens have a lot more growth hormone than we do as adults. Appears to play a vital role in adapting to the stress of resistance training. This diagram over to the right is growth hormone and cybernetic, cybernetic and interactions. Don't even worry about it. I don't even know why I put this in there. But the point I wanted to make to you is you see the pituitary gland there in white up top, part of the brain, and then you have the hypothalamus kind of stimulating growth hormone, which will literally make the body bigger. And it gets sent out to the left it stimulates fat mobilization. So growth hormone decreases your body fat. The next one says muscle. Growth hormone increases muscle mass. Over to the right, it says bone stimulating calcium accretion. So growth hormone will facilitate bone growth, and immune suppressing. So it'll stop some immune function in order to do all this stuff. And then we have one more hormone. It's called insulin-like growth factor, which works in concert with growth hormone. And that has a responsibility as well that we'll talk about in a second. Now, here's the main physiological role of growth hormone in its superfamily. So any kind of hormones in this world, they decrease glucose utilization, increase protein synthesis, so the rate at which your body can generate more muscle tissue or organ tissue or any tissue that is protein-based, increases collagen synthesis. So collagen is the stuff in our skin that makes our skin more kind of when you pull it, it responds. As we age, collagen production decreases dramatically, and that's sort of what I have in this picture here. Wrinkles and things like that are just results of less collagen in the skin, so the tissue can't respond. It can't rebound as quickly as it once did when we were younger. It also stimulates cartilage growth, enhances immune function, cell function, increases lipolysis or fat breakdown. So all of these things are a positive. You might have even heard of stories of people supplementing with getting growth hormone injections. It happens. And people generally start to say, like, my skin feels tighter. Of course it does. You're actually be able to build more collagen fibers in your skin tissue. They're basically fibers that hold and allow your tissue to hold its properties better. Joints feel better. Of course, because you're developing some cartilage, right? Which most of us are wearing away because we're not taking growth hormone. So there's a lot of benefits to this, but also remember that growth hormone will make any cell grow. So if you have high concentrations of growth hormone and you have some sort of bad cell, such as cancer, it can make cancer cells grow. So you got to work, if you're ever going to work, kind of look at some of this stuff and consider it. I'm going to recommend that you work with an endocrinologist directly, someone who's actually a medical doctor that has a fantastic understanding of all this stuff. But it's important to understand what these things do and how they can potentially go wrong as well. All right, so key point with growth hormone is that its release is affected by the type of resistance training protocol used, including the duration of rest period. So rest becomes a critical part of this. Short rest period types of workouts result in greater serum concentrations compared to long rest protocols or similar total work. However, at present, it's not very clear. It's not clear how the various molecular forms, aggregates, and splice variants. So these are all kind of sub-understandings of how the hormone itself interacts in the organization of the actual cell structure. Where is the structure? How is the structure put together? Or the types of growth hormone are affected by rest period duration. So it's kind of one of those things where we need more information on how this structure, how these things influence structure and ultimately work. It's still a work in progress. All right, so growth hormone responses in women, this is a really critical component because hormone concentrations and hormone responses to exercise vary with menstrual phase. Women, when they're going through having their period and they're basically getting rid of the lining of the uterus, there's a period after that where you've gotten rid of it and you have a new lining that's been built and ready to go. So you can see over here the menstrual cycle phases, and you can see that pink line. You see the estrogen increase, and we'll talk about estrogen in a minute. Luteinizing hormone, and then you have progesterone over here, and in the background is also going to be growth hormone, specifically close to kind of when we're building the new lining. That's when we're going to have higher concentrations of growth hormone. But however, it's still not fully understood how all of this works. So I'm going to leave a lot of that like we don't understand how it fully works. That's just kind of the way where we're at right now. Okay, training adaptations. There's Buddy over there. Growth hormone training adaptations. It appears that growth hormone concentrations need to be measured over longer time periods, 2 to 24 hours. So you have this window that typically you'll look at, let's say like a 24-hour window where you want to see you're not going to have the same concentrations of growth hormone. And you need to kind of capture, if you're ever going to kind of look at this, you would want to draw blood throughout different hours throughout the day to look at the concentrations of growth hormone. And in fact, most of growth hormone secretion is going to happen sometime at night. When we're kind of resting. So this is another reason why sleep becomes such an integral part of this performance dynamic, when we're talking about resistance training. The area under the time curve and this is also going to include arrays of what they call pulsatile effects. So that's just going to be sort of how this hormone is being secreted, tells whether changes in release have occurred. And, ultimately it's like, is it happening or not? It all depends at the time of day that you actually take the serum concentration, and you really should be tracked over a 24-hour period. Now we have insulin growth-like factors. So it's a little different hormone. Human growth hormone on the left in the first bullet point initiates the growth process, while insulin growth factor 1 carries out many of the growth promoting actions. They work together in complex hormonal systems to regulate growth, development, and metabolism. Responses of insulin-like growth factor 1 to multiple sets, heavy resistance exercise protocols on 3 consecutive days with and without nutritional supplementation of protein carbohydrates before and during the 1 hour recovery period. So you're going to see day 1, day 2 in this picture, day 3 at the bottom. You're going to see on the left, the concentrations of IGF-1, and you're going to see day 1, we get some increase. Day 2, we have a significant increase. And then day 3, we still have an increase and it starts to taper down. So this could be an argument for getting your full body training done at least 3 days a week. And I can tell you anecdotally, working with clients, we say 2 days a week is the minimum that you need to do full body training to stimulate adaptation. But 3 days is much more optimal. Part of it is, and I've seen people when they get that third day in, how much more rapidly their body physique transformation happens. Part of that is going to be some of the results of our hormone concentrations being better suited because of that third day of stimulation. All right, training adaptations of insulin-like growth factor, probably reflected in a variety of mechanisms related to the type of insulin growth factors released, transport, and receptor interactions. Kind of goes par for the course with hormones. Interaction with other anabolic hormones cannot be ignored, as these often target the same outcome, right? So some hormones are going to do some very similar things. Adaptation to heavy resistance training in IGF-1 in the various tissues still requires further investigation. So here we have our blanking on it. Gosh, it's been a long day. Sorry, but more research is needed, and this is the process of which we live. Don't have all the answers. So maybe one of you will be inspired one day to become an exercise physiologist and do some of this research. All right. Now, cortisol, now we're talking about adrenal glands. So adrenal hormones, the adrenal system, including adrenaline. Cortisol exerts its major catabolic muscle building effects by stimulating the conversion of amino acids to carbohydrates. So when we sometimes need protein for energy, like we were talking about in bioenergetics, cortisol is going to be responsible for that. That's the hormone that signals to do that. Increasing the level of proteolytic enzymes that break down proteins, inhibiting protein synthesis, so preventing protein growth, and suppressing many glucose-dependent processes such as glycogenesis or gluconeogenesis, where you're actually using other substances to make glucose and immune cell function. And it seems to have a greater effect on type 2 fibers than type 1 fibers. So here on the right-hand side, I've got a little quick understanding. We'll cover this in our functional anatomy class, our Kin Major 102. We'll talk a little bit more about structural differences in muscle fibers. And on the left is going to be your slow twitch type 1s that are really predominantly geared more towards oxygen consumption and mitochondria. They fatigue very slowly, but they're very small. Type 2As are going to be intermediate fast twitch. They're going to be a combination of oxidative and anaerobic, more glycolytic. So they're going to be using a little bit more sugar, as well as they can work in the oxidative world just like aerobics can. And they're going to be intermediate. And then we've got type 2Xs, which are going to be your super fast twitch. Those are going to be your anaerobic system. And fast glycolysis. So that, think of your big explosive lifts, Olympic weightlifting, 0 to 15 seconds type stuff. So you're going to see, though, that structurally they have a little bit of a different look, and they're different sizes. That's the big takeaway. But 2As can kind of move around depending on the stimulation, can look more like aerobic or can look more like type 2Xs, depending on the stimulation that you throw at it. And that's ultimately the response to your training stimuli. Cortisol, resistance exercise responses, response to resistance exercise protocols that create dramatic stimulus to anaerobic metabolism without oxygen metabolism. Increases in cortisol might not have negative effects in men after a period of training to which the body is adapted. So we sometimes have heard, cortisol is this negative catabolic hormone, right? It breaks things down, and it does because it allows protein to be used as glucose, and it's needed sometimes. But sometimes when we have a lot of stress, we can carry more cortisol in the system. But when we have a good history of of resistance training under our belt, the body can adapt and actually disinhibit cortisol at the level of the testes, thereby maintaining testosterone's primary influence on its nuclear receptors. So testosterone can have a greater effect the more time we have under training, because cortisol might be preventing the negative effects and helping to accelerate some of the testosterone production. Okay, so just I put that back in there. Cortisol anabolism versus catabolism versus anabolism. Catabolism is building, anabolism is breaking down. And then the key point here: resistance exercise protocols that use high volume, so more reps, more sets. So instead of like 3 by 10, maybe I do 6 by 10. And short rest periods, right? 30 seconds to 60 seconds through chronic high increased serum cortisol levels. Though chronic high concentrations of cortisol may have adverse catabolic effects, acute increases still contribute to the remodeling of muscle tissue and maintenance of blood glucose. So if we have that, as I said before, high levels of cortisol, especially if it's stress-induced, that can be negative long-term. We don't want high concentrations over the long term, but during this catabolism, anabolism breakdown phase, we're going to need this cortisol. It is an essential component, an essential hormone to this entire process. All right, catecholamines role. So these are going to be your other adrenal hormones. They're going to increase force production via central mechanisms and increase metabolic enzymatic activity, increase muscle concentration rate, right? So, contraction rate. So getting the muscles to actually work harder. Think of adrenaline, right? Just basic adrenaline. I'm running on adrenaline, right? Your body gets primed up to do more work. So all of these positive things happen. Increased blood pressure, right? If I increase blood pressure, I can get the system to prime and ready to deliver vital components to the muscles to do their job. Increased energy availability is going to allow me to work harder. And then increase muscle blood flow via vasodilation. So vasodilation is when the muscles, the circulatory system, the veins, the vessels, they get bigger. The arteries get bigger, so more blood flow can pass through there, providing you more of the necessary elements to do work. Augment secretion rates of other hormones, such as testosterone. So it's going to just say, hey, we're in fight mode, we got to go. Catecholamines training adaptation. So heavy resistance training has been shown to increase the ability of an athlete to secrete greater amounts of epinephrine during maximal exercise. And think of epinephrine as adrenaline, but it's epinephrine. Because epinephrine is involved in the metabolic control, force production, and the response mechanisms of the hormones, such as testosterone, growth hormone, and IGFs, stimulation of the catecholamines is probably one of the first endocrine mechanisms to occur in response to resistance exercise. I put this epinephrine injection because some of you might know, you're like, hey, I'm allergic to bees. I have an EpiPen. You might have heard that, right? And epi is just going to basically prime your body to do all of those other things that we just talked about on the previous slide, to be ready to fight and vasodilate your airways, your circulatory system. Because if you have an allergy reaction to, let's say, a bee sting, all of those things start to close up. Epinephrine works against that and puts you into the fight scenario so that you can actually function. Other hormonal considerations, such as insulin, thyroid hormones, and beta endorphins, have been implicated in growth, repair, pain, analgesia. So, as in like an analgesic, meaning its pain goes away. Exercise stress mechanisms. Unfortunately, there's limited data concerning their responses in the adaptations to resistance exercise or training. So we've got this whole amazing system, the adrenal system here, and we still are just scratching the surface from a performance perspective of how all this stuff really works. All right, questions. I'm going to have you go to the discussion board. We'll put up another discussion question situation over there. I like the interaction. I'll respond vis-a-vis video. It's just easier. But I do think it's a nice way to have you learn something, kind of go through it, sit with it, think about it, and then actually answer some of the questions that maybe I just didn't get to because I didn't think to do it. So have you jump over to the discussion board with any questions. All right, talk to you soon.